of our college. In this moment, he is always with us whenever we require. We cordially welcome him. Also, some faculty members of the college are present here in this moment. I welcome all of them. Today, three invited speakers are going to deliver their speech. We are very much pleased and delighted to have a great personality like Professor Samal Kumar Mandal, who is a professor and HOD in the Department of Applied Mathematics with Oceanology and Computer Programming at Vidyasagar University, Midnapur. Professor Samarjit Kaur is the professor in the Department of Mathematics at National Institute of Technology, Durgapur, and Dr. Borun Das, who is an associate professor in the Department of Mathematics at Sidhu Kanu Birsa University, Purulia, are among us. On behalf of the college and organizing committee, I heartily welcome all of them. This is a difficult situation. A global pandemic situation is around us. COVID-19 is spreading exponentially around the world. No medicine till not be found. Although Russia has declared they had found a vaccine for this, but till now there is a controversy going on. If it is supposed to globally acceptable, then there is also a long time taking procedure to follow to reach the vaccine to our market. And if it is not acceptable globally, then we don't know when it is coming. So we don't know what is coming in our near future. In this present scenario, some mathematicians are fully engaged to characterize the behavior of the coronavirus. Some models have been developed. Some are working on the effect of pandemic in the real life situations. So in this webinar, we are going to discuss such kind of discussion. This is our first effort to conduct a webinar in our department. And to start the program, now I request Dr. Uma Bhumi, principal of our college and chairman of this webinar organizing committee, to deliver a short speech. Madam, please. Madam কে একটু করবেন, please deliver. Madam, are you present here?
Hello?
Yes, madam is there. Hello.
Huh?
Yes. Ma'am, please deliver your speech or I will open the video.
No, you can open the video. When I just
Oh, ma'am told me that to the short speech in the video, I am opening the video. Okay, I am sharing the video of the speech.
Good morning. It is my pleasure as the principal of Vivekananda Satavarshiki Mahavidyalaya to welcome you, all the dignitaries present in the webinar Application of Mathematics on Epidemiology, organized by the Department of Mathematics of our college. At present, every aspect of local and global situation and education suffers from the crisis of COVID-19. The outbreak of coronavirus has caused problems in the functioning of all countries of the world. This affects badly to global economy, health, and particularly our education system. The rule of social distancing is continuing in accordance with the standard operating practices. We are getting frustrated and waiting for the situation when everything will be normal. We are following everyday statistics regarding the rate of infection, death, and the recovery. There are several questions playing in our mind whether these are increasing or decreasing, whether there is a saturation in the rate of death or infections. Every day we are waiting to hear that we have arrived at the peak of infections or deaths, and then for the time being situation will be normal. Scientists all over the world are engaged in finding the remedies and recoveries from this pandemic situation. Mathematicians are also engaged to explore the statistics through the mathematical modeling. The term epidemiology is used in mathematics to mean method used to find causes of health outcomes and diseases in populations. Biomathematics is an interdisciplinary field that uses mathematical techniques and tools to model natural and biological processes. Now, mathematicians all over the world are working in the field of epidemiology, which is also a part of biomathematics. Today's webinar is very much relevant in context of present pandemic situation. Today, I feel honored to have three renowned mathematicians with us. Professor Samal Kumar Mondal, Head and Professor Department of Applied Mathematics with Oceanology and Computer Programming, Vidyasagar University. Professor Samarjit Kaur, Professor, Department of Mathematics of NIT, Durgapur, and Dr. Borun Das, Associate Professor, Department of Mathematics, Sidhu Kano, Birsa University. It is a pleasure for me to welcome you all. We are very much grateful to you, sir, for giving us your valuable time. Hope that your valuable lectures will provide us useful ideas and new dimension in this area even in this pandemic situation. I have also realized that there is a remarkable participation in the webinar, joining with great enthusiasm. I am thankful to all of you to be with us in this journey. I am also thankful to our organizers, Dr. Karthik Patro and Professor Rahul Mondal, associate professors in the Department of Mathematics of our college and conveners of today's webinar. Overcoming a large hardship and giving a tremendous effort, they are successful to arrange this. Hope that we will enjoy the webinar and be enlightened. We are all very excited to listen the speakers, so without spending no more time, wishing all of you with good health and prosperous future, I request Dr. Karthik Patro to start the session. Karthik, please.
Thank you, madam. Now I request Mr. Rakhovari Pal, Associate Professor of Vivekananda Satavarshiki Mahavidyalaya, to deliver a short speech. Please, sir.
আমাকে দেখা যাচ্ছে? হ্যালো,
হ্যাঁ স্যার
দেখা
বলুন।
যাচ্ছে? হ্যালো, আমাকে দেখতে পাচ্ছো?
স্টার্ট স্যার। your video is not on. Okay, you may start, sir.
Start. Okay.
Okay.
স্যার
Respected.
আপনি ভিডিওটা অন করে নিন স্যার, স্টার্ট মাই ভিডিও করে নিন, মাইকের পাশে রেখে
আচ্ছা ওকে অন হয়েছে?
No, no, no.
নাও
হ্যাঁ স্যার
Yes, yes.
এসছে।
Okay, sir. Before starting, I want. Okay, okay, sir. You start.
ওকে। Respected Chairperson Dr. Uma Bhumi, Principal of Vivekananda Satavarshiki Mahavidyalaya, and Joint Convener Dr. Karthik Patro and Professor Rahul Mondal, faculty members Rajiv Lochon Pramanik, Arindam Singh, and our valuable resource persons, Professor Samal Kumar Mondal, HOD, Department of Applied Mathematics with Oceanology and Computer Programming, Vidyasagar University, and present Sir Professor Samarjit Kaur, Professor, Department of Mathematics, NIT Durgapur, Dr. Borun Das, Associate Professor, Department of Mathematics, Sidhu Kanu, Birsa University, and all other administrative staffs and my students. It's a moment of great pleasure and honor being invited to deliver a speech, special speech in the webinar named Application of Mathematics on Epidemiology. In this program, the organizing professors, Professor Manoranjan Maiti, I convey my best regards to Professor Manoranjan Maiti and all other organizers. Today, it is a great situation of pandemic coronavirus. Communicable diseases have always been an important role in the history. Since the beginning of the recorded history, there have been epidemics that have invaded populations after causing many deaths before disappearing. Now, in the current situation, world is going to a tough condition by the attack of coronavirus, which has already killed near about 1.25 crores of people of world. To check this pandemic situation, scientists, mathematicians, doctors, all other scientists try to discover something to check this coronavirus. I, in this respect, also tell some mathematical talks about it. In this situation, we have heard that different government, state government has taken the model from the mathematicians. These models are designed the biological parameters. The parameters are given by biology, and these parameters are fed into the model. Such type of model is known as SIR. S means susceptibility, I means infectious, and R for recover. In this model, some mathematical phenomena are used, such as difference equation and differential equations. Difference equations are worked on the discrete level, and differential equations are used in the continuous level. Continuous level. Acha. SIR is the more basic model, after which some advanced models are also used. With this SIR, vaccination is introduced in this model, and this type of model are known as SBIR. Acha. How math is used in epidemiology? Epidemiologists used mathematical model in order to track the progress of most infectious diseases. They may also discover the likely outcome of an epidemic or to help the process of vaccination. Acha. In the epidemiology, there are 5 W's. One W is what? Mane, what is the health event? Who? Mane, person related to this infectious disease. Where? Mane, place. Where the disease occur. When? Means time. Why? Mane, causes. With these parameters supplied by the epidemiologists, and which are used in model, and the differential equation used to calculate the basic reproduction number R naught. It is the basic model that help us to determine whether a pathogen will die out or not. Next, I am going to discuss the mode of propagation of coronavirus. Coronavirus or any other virus, SARS. SARS has told near about 5 crores people throughout the world. The growth of this disease is called exponential growth. Exponential growth means it is a rapid growth with time, and after certain months or after days, it will come to a plateau. After that, it becomes downwards. This type of curve is also known as logistic curve. I am not going to the details of model or mathematics involved in this model. These words, but these talks will be heard from our resource persons. Achha. Now there is another thing. Logistic model is quite the problem. And no more. I thanks to my colleagues, Dr. Karthik Patro, to invite me in this webinar, and Madam Chairperson of this webinar, and also I grateful to Dr. Samal Kumar Mondal and my beloved teachers, Dr. Monoranjan Maiti. Thank you. Okay. Karthik. Hello,
Yes,
Karthik.
sir. Yes, sir. Yes,
Okay.
Sir. Thank you, sir.
Okay.
Now we are going to start our lecture session. So past speaker of this session is Professor Samal Kumar Mandal. Uh, so before starting the program, I want to announce to all the participants to mute their microphones at the time of presentation. Also, don't share any screen at the time of presentation. This is my request. Now, Professor Samal Kumar Mandal is a professor and HOD in the Department of Applied Mathematics with Oceanology and Computer Programming at Vidyasagar University. He was a gold medalist at Vidyasagar University at UG and PG level. He completed his MTech degree from ISM Dhanbad. He completed his PhD degree from Vidyasagar University. His research interest areas are biomathematics, inventory, supply chain, soft computing, risk analysis. He has been doctoral dissertation advisor to 14 students as of now, and 6 students are working currently under his supervision. Also, 4 has been faced their pre-submission seminar. He is working in this department from 2004 and working as a professor till 2015. Visited Vietnam, Thailand, Bangladesh to deliver different speeches in different international conferences. He has more than 150 international publications in different reputed journals like in Journal of Cleaner Production, Transportation Research Party, Logistic and Transportation Review, Applied Subcomputing, Journal of Industrial and Production Engineering, Computers and Industrial Engineering, and also Operation Research, Chaos Solution and Fractal, Information Sciences, Nonlinear Dynamics, etc. His article has been cited more than 2,200 times on Google Scholar. Today he is going to deliver a speech on nonlinear differential equation in spreading of communicable disease. So I request Professor Samal Kumar Mandal to start his session. Sir.
Good morning. Good morning to all. Good morning, respected persons. This one-day webinar. Principal Dr. Uma Bhumik. And special thanks Joint Convener Dr. Karthik to give me opportunity to say something in this webinar. Another Joint Convener, Sri Rahul Mandal, Assistant Professor in this department. Thanks, former Professor Rakho Haripal. He also present now in this webinar. Thanks other dignitaries, resource persons, faculties in the college, and my beloved participants, students, research scholars who attend in this webinar. So thank you all and good morning. Basically, you all know we are now in stagnant conditions due to COVID-19. So this is critical situations very now. We are all staying in our home. All educational institutions are closed till date. We don't know when everything will be normal. In this respect, organization of such types of webinar is very fruitful. Title is, I think, application of mathematics in epidemiology. Basically, I am a small person in this area, but I'm giving some basic knowledge to our students, to our research scholars. Basically, new research scholar, just who want to get started their research, does not decide in which field you want to work, want to research for that persons. So this is very interesting area, also useful area in our society. Since we are all mathematicians, we are cultivate mathematics in our daily life with our students, with our colleagues. So we are trying how mathematical tools can be used to overcome such situations. So now I just going our lesson. So I sharing my file with you. Of which will be discussed today's lecture, today's session. Nonlinear definition in spreading of communicable disease. I am Professor Samarpan Mandal from Vidyasagar University. So before starting, look at our previous records in the area in which epidemiology started. Before that, review what is meaning by epidemiology. It is derived from Greek word. Basically, all scientific, basically Greek, that is very rich in. So epidemiology, that is has. What is mean by epidemiology? There are three meanings. You see here, epi, demi, and ology. Epi means upon, that is people, populations. That means scientific study. That means epidemiology means scientific study upon people, upon population. Scientific study population, people or population. That means what types of study in populations, human populations? Basically, so it means that the scientific study of the disease pattern in human populations, how disease can be spread from person in our society, that can be studied in science. In which branch? That is known as epidemiology. So there is human health, and what is the effect of all factors that can be studied. So it is obvious that from this term epidemiology and meaning of this epidemiology, this is actually multidisciplinary subject, multidisciplinary, and more than one discipline is involved in this area. In this area involved that persons who are physicians, doctors, biologists, health experts, health educators, mathematicians, etc. Persons is involved, and everyone trying to enrich in this field in such a way that our society, that means human, is they can save in their life. This is the epidemiology. This is the topics of this seminar, title of this seminar, webinar. And if you see, if looked out the history, we see that it is started 460 BC, before Christ. That means birth of 460 years ago. of birth of Jesus Christ through the scientist Hippocrates. At that time, Hippocrates studied different things on human health and human behavior. What is the effect of environment and human behavior? Human health. That has been studied. After that, 16th John Ground, what birth, death with. Then 1747, so that what is the effect of fresh food? The of fresh food to treatment of scurvy disease has been discussed in his work. 39. William Clark. He established statistics for the evolution of health problems. 1854. John Snow. He tested on the origin of epidemic of cholera. That means what is the source of cholera epidemic? How these types of epidemic is generated from that source. On that, some hypotheses had been tested by John Snow. Then Alexander Lewis, 1872. He did systematize the application of numerical thinking. After that, 1937, Bradford Hill. He suggested some criteria for establishing positions. So, the beginnings of epidemiology, we see that there are 7 landmarks in the history of epidemiology. With their hands, the epidemiology, the research had been started. And we see in epidemiology, there are 3 things. One is host, who invites actually disease through agent in some environment. So 3 things are there: host, agent, and environment. Our basic things in epidemiology to construct a model to study the health problem. And in this study about health problem, there are 3 factors: host, environment, agent. And it is seen that here disease is produced by exposure of susceptible host to an noxious, that is harmful agent in the presence of suitable environmental factors, which aid the agent of disease, which hinders the agent of the disease. So we see the triangular relations in epidemiology: host, environment, and agent. Now, why we are discussing epidemiology? Now, what is the aims of epidemiology? According to International Epidemiological Association, there are 3 main aims. 3 goals are there on the basis of this association. First one is to describe and analyze the disease occurrence and distribution in human populations. That means in human populations, how the diseases are occurred, and how the diseases are distributed, that is transmitted from one person, one people to another. That description, that analysis is very important. That is the of this association. Next one is identify etiological factors in pathogenesis of the disease. Yet, what is these things? Now, that factors, that cause, things which causes is, that is, factors we have to identify by which this disease is caused. Third one is, from these discussions, from these investigations, we have to provide some information which are very essential to the government. Implementations for what purpose? For prevention and control and treatment of the disease. So these three are the. So basic is that basic aims actually to eliminate or reduce and its consequences and promote the health and well-being. Now how stay in good conditions in our society, that can be confirmed. That is the aim of the study of the epidemiology. So main thing is regarding the health and our aims, our populations, our human beings to keep in safe place, in safe position in their life. That is the main goal of the studies. So already I told that multidisciplinary area, multidisciplinary subject, different persons are in, and it is used differently in different areas, such as economics, statistics, and so on. So according to their useness in different fields, there are different classification of just be mentioning, not discussing in detail. That is epidemiology, geographical epidemiology, social epidemiology, statistical epidemiology, descriptive epidemiology, analytical epidemiology, experimental epidemiology, and infectious disease epidemiology. So different kinds of classifications are in which different persons in different expertise are doing work. Keep the human beings in a safe positions. So, but we are now all mathematicians. We are all mathematics, discuss, cultivate research in mathematics. So we have to see how mathematical techniques can be used in to give some information in our society, in our government, in such a way that our nation remains in healthy conditions. So basic mathematical models. In this area, actually started by some, there are very renowned scientists by whom modeling epidemiology had been started. First one is known in 1760. He first formulated and then solved a model. Smallpox, you know. Once upon a time, it was also epidemic. So in his model, he evaluated the effectiveness of inoculating of healthy people against small virus. That is the starting point of our mathematical. After that, Hammer, 1906, he also formulated and analyzed to understand the epidemics. That is how frequently measles disease can be occurred in persons. Regarding occurrence, that has been discussed, analyzed by Hammer. Then 1911, Ronald Ross, you know, British doctor. Actually, he got the Nobel Prize in physiology or medicine in 1902 in transmission of malaria. That person's developed a differential equation model. After that, and McKendrick, 1926, he extended Ross model, and also he obtained some important results, that is epidemic. So these are the starting. After that, nowadays and recently, different researchers throughout the world are working in this area on different side of epidemiology. They are all always trying to give some insight of these aid and water. But in this lecture, I want to give the basic idea how to do research, but what is the role of mathematics, but how to build a mathematical model gives you that clarifications. You see, there are three entities: biological problem, mathematical. So we see that epidemiology, basically that is the biological problem. So first of all, we have to study it, we have to explore very carefully the biological phenomena of that disease, then that problem, that physical biological problem, imposing some assumptions, obviously you have to impose some assumptions. Imposing some assumptions, we have to construct a mathematical model. That is biological problem with respect to some assumption that is converted the mathematical model. Without assumptions, it is not possible to construct the mathematical model. So we have to consider this assumption. We have to take all that types of assumptions which are realistic. Here, mimic so after the construction of mathematical models, as a mathematicians, what should do? We have to get the solutions. We have to analyze these models to get the solution. How? Using some mathematical tools, mathematical techniques. After getting that solutions, we have to get the predictions about these biological problems through simulations, and then compared how much prediction with the physical problem. This is the actual scenario in our brain. And in these thinkings, all remember, we have to build up, we have to develop mathematical tools to solve it. Now we're going the mathematical models. Meaning of epidemiology. Again, we are seeing here also to give the trace on this area. Basically, it is the discipline which deals the study of infectious disease in a population. It is concerned with all the epidemic, all aspects. That is, how it is spread, how to control, is there any vaccination strategy or not? Everything. And as a mathematician, as a mathematical researcher in this field, our aim of this epidemical modeling is how fast the disease spread, how much is infected or will be infected. Is there any control measure to stop the spread of the disease or not? How control strategy can be implemented? Is there any effects of environment on ecology or not? In our society, these types of query investigations actually we are doing through these mathematical models. There are two types of infectious disease: acute or that types of infectious disease which stay for a short period, that is influenza, chickenpox, etc. and chronic infectious disease that is stay for large period, that is hepatitis. That is just classifications of infectious disease. And for modeling in this area, we have to always take care about the spread of infectious disease. And spread of infectious disease basically depends upon four things, basically. Susceptible populations, immune class, and mode of transmission. Susceptible populations, that means in our society, all members, in a community, all members are susceptible. That person, that populations in which the disease is not exposed till now, that is that person population is susceptible. When the disease is exposed, that is known as infected. Symptoms, that is the infected by infective populations. Then the immune class, that is recovered class. After infections, that members of the populations and recovered, that belongs to immune class. Three classes there. And very important is the mode of transmission. How the disease is transmitted from susceptible to infected. So these are the important criteria. So here we discuss some model. Very simple model. Since you want to discuss the basic things. This is SI model actually. You see, S for susceptible, population of susceptible, I for infected, population of infected. Both are function of time, because when time progresses, population of infected, the density are changed. So what is the how much person, how much members are transferred from susceptible to infected? Here, since we are mathematicians, so we have to consider a parameter. Here beta, that is known as average number of contact between susceptible and infected. So if we model it, so we have ds by 2 minus beta si and di by dt equal to beta si. That ds by dt, that is rate of change of susceptible person, susceptible density. That will be changed at the rate of which that's amount which are from susceptible infected. That amount is beta si. Since beta, it depends on S and I, because infection will be occurred at that time that infected persons is contact with the susceptible persons. So in this is beta si. So ds by dt equal to minus beta si. The rate of increase of infected will be obviously di by dt equal to. So this is the SI model. Very simple differential equation. You see, model SIS model. In this model, it is considered that susceptible to infected at the rate of on a per unit time, beta Si amount are infected, and after recovering, that persons in this regard rate of change of that is gamma I minus beta Si. Gamma I after recovery of persons, susceptible persons, so it increased the rate of gamma I, and from the susceptible beta Si amount of members are going, that is infected to beta Si. So this is the another model equal to gamma I minus beta Si and di by dt equal to. This is another model. If I have here three things: susceptible, infected, and recovered. ST susceptible, IT infected and recovered. Susceptible to susceptible from susceptible populations. This amount of members getting infected. So at this rate of infection, infected person increases. After that, after treatment from infected person, infected population, this amount of persons is recovering. dr by dt equal to gamma I. So this is the model, another differential equation. It is also, and this is also SIR. But updated, considering some extra phenomena. What is that? Actually, the population is constant, but susceptible rate of susceptible, that is increases V that indicate the birth rate with passive immunity. So it belongs. These things is new. This is incorporated in this model. Another thing is that in this model there was no consideration a normal death rate of the population. Normal death rate. Here, normal death rate. Either it may be susceptible or infected or recovered. The normal death rate has been considered. This is the death rate per unit time. Per unit time, this amount of members have died. Here, this amount. So, we see the upgradation of the model, incorporating some extra phenomena. This is the actually research. Those persons are doing research in this area. Every time they are thinking how this model will be more realistic, incorporating some real phenomena, which will be more realistic before God. This is the work of researchers in this area. So, what we are saying in the discussions of this model, two things we are seeing. One is biological concept, and that concept, biological concept, is converted mathematical concept, mathematical model, a set of differential equations. So ultimately, we are getting a set of differential equations. So there is nothing but a differential equation. So we have to, we know what is the significance of differential equation. The basic attention, basic goals, the differential, how to solve it. What is the physical meaning of a differential equation? For illustration, we consider a simple, I think it is very trivial to you all. It is very trivial differential equations. Dx by x. You are studying, I think, from higher secondary level, how to solve these types of differential equation. Everybody knows. So what means dx by dt equal to x? You know these things. What is x? That is actually unknown. Unknown real functions of real variable t. Dx by dt, that is derivative, you know. A is parameter, you know also. So you are seeing for different values of A, you got different differential equations, different values of A. A is the parameter, that is important things. Parameter is important things. That is the main thing, main studies. You are seeing, yeah, different types of parameters are here. mu, beta. As a mathematician, we have to consider to construct the model. But what are the effects? Parameter, that is very important to study in this area. Values of A, you get in the different differential equation. So different solution. Solution, general solution, you see. You see, what are the nature of these solutions? When the values of A varies different scale, different. When you see, when A equal to 0, and A, the parameter value equal to 0, you got these solutions. Xt constant, xt equal to constant. If k equal to 0, xt equal to 0. Equal to 0. That is xt equal to 0 by xt equal to constant. To constant, you know. Yeah, what is called these types of solutions? Xt equal to constant. This is constant solution. Constant solution basically equilibrium solution. Equilibrium solutions is known as equilibrium solutions. Equilibrium point in this equation. Equilibrium point in this equation. Yeah. Constant solution x equal to 0. That means for all time x remains same, x constant. That is the equilibrium solution. That is important. So equilibrium point is the important concept in this area, equilibrium point. We always study analysis with respect to equilibrium point because the solution is that solution in which case the variable, unknown variable, that means population density or number of susceptible persons, required persons, affected persons, that will be constant, remain same for all time. Time progresses, but that is same. Here, pictorially, we see here x equal to 0. This line, actually, this is not clearly visible. This is x-axis. So this t-axis, that is the x equal to 0. That is the x equal. That is the equilibrium line, equilibrium solution, equilibrium point. For all time, it is same. When a equal to 0. When a greater than 0, you see, when a greater than 0, if k positive and t progresses, t advances, t goes to infinity, then this value xt to infinity, minus infinity, plus infinity. That is, you see, when a greater than 0, that is, you see, when a greater than 0, all solutions, you see, all solutions tends away from equilibrium solution. All solutions tends away from solution, away from equilibrium solution. When t progresses, t advances, but when a is negative, in this case, when t tends to infinity, time advances in forward direction, advances, then xt actually tends to 0 for all cases, either k positive or k negative, or k equal to 0 or positive. That means, what is the physical meaning, the geometric meaning of this solution, of this differential equation? You see, in this case, all solution tends to equilibrium point. All solution tends to equilibrium point. But t-axis is the equilibrium point. So, in this case, when a positive, the equilibrium point is known as source, because from that point, all solutions tend away from that solution. That is the source known as. But here, you see, when t progresses, all solutions goes to equilibrium point. That is sink. That is known as sink. So you see, this is the analysis. But this is not only work. This is differential equation just to get the solution. That is enough. That is sufficient. Not the study. That is not the analysis. Analysis is which are involved in the differential equations. What is the behavior? What is the behavior of all solutions with respect to the equilibrium solution, equilibrium point? And you also see that when a equal to 0, you get the equilibrium solutions, and you change the value of a slightly. You change the value of a slightly, you see, there are huge change in the solution structure, solution behavior. In this case, it will be this side, and this case this side. So solution is changed or due to small change of the parameters. That is the bifurcations. That is the bifurcations about the equilibrium point due to the parameters. The bifurcations, that is the important concept to study in this area. So this is the differential. So this is the thing actually which are studied in mathematical model. That is very simple. One thing that You see all differential equations which are involved practically such types of epidemiological model, not linear. Most of them are nonlinear differential equations. Differential equations, you know, linear differential coefficients can be solved very easily. Solution for linear differential equations. It is not confirmed. Basically, it is not possible to equation analytically. This is the blame to us as the mathematicians. Differential equation you cannot solve classically. There is no method. Basically, such types of differential equation belongs to dynamical system. No dynamical system. Dynamical system means the system, the pace. Basically, it is the passage. It is the passage with respect of all points in space. The dynamical system. With respect to time, if time considered discrete, that is discrete dynamical system. Is continuous dynamical system. How to solve such types of problem? This is actually one method, that is null Klein. Null Klein is one method concept to solve nonlinear differential equations. It is treated as we are applying these things in a model which is also previous shortly described, but here we have spread of communicable disease, spread of maybe model in nonlinear differential equation. Here we consider simple SIR models. Basically, in this model, population in the society, in the community, three decision groups. One group, one set, that is susceptible individual, that is S, infected, that is I, recovered R. You already know. Function of time. Why function of time? It is also you know. But here, already we see that every biology can be constructed the mathematical model with respect to some assumptions. Here also we can assume on assumptions. Assumption is that the total population is constant. Total population in the community is constant. That is, there is no consideration of birth and death. Birth and death. That is S plus I plus R. That is the total population in the community. That will not change. That remains fixed. So d by dt of important assumption is that in this model, the one individual has been infected. Once an individual has been infected, subsequently it has been recovered. If that individual is recovered, that cannot be reinfected. It is the important thing. And after one in future, further, that person will not be infected. Not that is the important criteria. After recovery, so that person cannot belong to susceptible class. That is important. These types of basically occurs in the disease, measles, mumps, smallpox. You know smallpox. In past times, in our society, it is a epidemic. You know that if once a person is infected with smallpox, yeah, his or her life, that person would not be affected with the smallpox. Consider. Then rate of transmission of disease, obviously, that is proportional to the number of encounters. So mathematically, these assumptions can be right. ds by dt equal to decide, we know already. And we have to also consider rate at which infected individual recover, proportional to number of infected. So this is the model. And we have to, this is the, and you see already you have this information. And you see here SIR, C variables. But you can convert these set of three differential equation to two differential equations, because here you see dr by dt equal to gamma I. So if you get the I, obviously solve dr by dt equal to gamma. So it is not required to solve. So you have to record the initially analyze ds by dt equal to this and di by dt equal to this. So and first of all, we have to find out the equilibrium point. Equilibrium point. What is the equilibrium point? You know, equilibrium point, that solutions which will remain same for all time. That is ds by dt equal to 0. This thing equal getting 0, this and this one, you get the equilibrium point, that is the given by s axis. You see here s axis. S axis. So s axis, that is not a single equilibrium, that is set of equilibrium point, that is s axis. After that, since it is nonlinear differential equations, it is not possible directly solve the nonlinear differential equation. One technique is that linearization. Linearization. There is a technique. But nonlinear differential equation to linear differential equation. Next, we get this matrix. This is known as community matrix. This is the matrix. At this, and then from this matrix we get the eigenvalues. Two eigenvalues is there. This and this one. One is 0. Other is this one. And this eigenvalue either positive or negative depending on the value of this. So what is the condition? Actually, basically, in theoretically, we know that if eigenvalues have negative real part, negative real value, then the solution is stable. Solution is stable. That means all other solutions except equilibrium, all other solutions actually near to equilibrium solutions. So, but here this is 0 and one is 0 eigenvalue, another negative or positive, so it is not confirmed. Technique here. That is known as null clients. Null clients. What is null client? This is the null clients. There are two null clients here of this differential equation. S null clients, which will be obtained from this, and I null clients from this. What is these things? S null clients means S null client, that is the set of points at which ds by dt vanishes. ds by dt will be 0. Points, that points is the set at which ds by dt 0. That is, you get S null client equating these things is 0. And I getting this 0. So you see S null clients from here, S equal to 0 and I equal to 0. S equal to 0, I equal to 0. That is x axis and y axis. S axis, this axis and this axis. That is on this line and on this line, ds by dt 0. ds by dt 0. That is rate of person 0. There is no change. And here I-axis, you see here I-axis, that is the S clients. On this I-axis, ds by dt is 0. But what is the status of di by dt? What is the status of di by dt? What is the value of di by dt? Di by dt equal to minus gamma. Di by S is 0, so di by dt will be minus gamma. Di by dt will minus gamma. Di by dt. That is indicating these things. This indicating that dt minus, that means I decreases. That is, solution tend to origin along this line. Solution tend to origin along this line. This is the exploration. Again, I null clients. If you consider I null clients, I null clients should be obtained from here. Di by dt equal to 0. That is this. That two solutions will be obtained from here. One is I equal to 0 and another is S equal to gamma beta. So I null clients I equal to 0. I equal to 0 means this line, and gamma beta, that is another set of points. Vertical, this is vertical line, this line is equal to gamma beta. So these are two null clients. You see this line, on this line and on this line, di by dt 0. dt equal to 0. So from this figure, you see that if initial populations, that is populations is with some members. Here, initial population, that is S0, I0, where S0 greater than gamma beta, I0 positive, obviously. Part. If initial solution, initial population is here, if population started from this point, what will be from this figure? You see that first of all, susceptible population increases, decreases. Susceptible population decreases monotonically, while infected populations at first rises and eventually reaches maximum. Is it clear? Initially, population start with the values which is stated here in this part. So when the population started with that value, if you see that, if you observe that, susceptible persons initially decreases. Susceptible persons initially decreases. You see the direction of decrease, direction. In this direction, this population's solution is going on. Populations in this direction. So susceptible is decreases, but infected is increases. And ultimately, on this line, it reaches the maximum. After that, it is decreases. So how it is obtained? Actually, how it is, or how this direction it is obtained? That is very simple. That is very simple actually. You get a point in this area, any point you get in this path, in this area, and at that point you find the value. You find the value ds by dt and di by dt. At that point, you determine what are the value of ds by dt, just putting the value s and I. Since already you get the point ds by dt. So you have got 2 points, 2 values, ds by equal to something and di by dt equal to something. Suppose ds by dt equal to 2 and di by dt equal to 3. 2, 3. Informations give you what? Now this information give you vector field, because ds by dt indicates the change, the slope of the change, ds by dt and di by dt. So that is the actually vector field. And if you value it, the vector field is these directions. If you point here, you get this direction. If you point here, you get this direction. So if you construct the figure completely, so you have types of directions you have, which is known as phase portrait of the SIR system. Here you see that ultimately concluded that population eventually infected population declines to zero. Infected, first of all, infected increases, susceptible decreases, get the maximum value. After that, it is decreases. So it declines to zero. This is the actual analysis. I am not getting more time. There also another model is there. I have not discussed due to lack of time. And on this is my reference. And through these deliberations, I want to convince all participants that actually there exists beauty in mathematics, in mathematical tools. But we have to know how to get this beautiness. For example, we see here how this picture is drawing using mathematics, and from which how we can draw the conclusions. Because linear system cannot be solved directly. Why? Nonlinear system cannot be solved. There does not exist solution because lack of appropriate functional, we not getting the solutions. So techniques is there in this area. That means dynamical system, set of differential equations, which can be used to study biological physical problems, through which we can contribute some information to our society, to our nations, to the world. Researcher will be motivated through this lecture in this area. Thank you, organizer. Thank you, Kartik Babu. Thank you, principal. Thank you, other staff in the college, and thank you, all audience, for listening my lecture. Thank you all. Kartik,
Yes, sir.
this is my end of lecture.
Oh, and I want to. Is there any question to the sir? Is anyone? Okay, if not, then thank you, sir, for your nice presentation. And this was very nice and simple presentation. I think this lecture help us to enrich our knowledge. All the participants, here are some student participants also who are studying the nonlinear dynamics, initially basics, and basics are discussed by the sir. So I again thank Professor Samuel Kumar Mondal for such nice lecture. Next, the next I want to go to the next speaker. The next speaker is Professor Samarjit Kaur. So please, sir, deliver your lecture.
Hello, Karthik. Can you hear me?
Yes, sir. Yes, sir.
Okay.
Let's start.
Okay. Just first I
স্যার
share my
আপনার
screen.
ভিডিওটা সম্মুখীন স্যার
Just a minute.
স্যার স্টার্ট ইউর ভিডিও
Start my video. Is it okay? Hello.
No, sir. Your video is
ভিডিওটা ভিডিওটা স্যার
no, sir.
এখনো
Your
আসেনি
video is not coming.
Video টা আসেনি না? না, না।
No, no, sir.
We cannot answer. ভিডিওটা আসছে না কেন?
স্যার নিচের দিকে দেখুন স্টার্ট মাই ভিডিও
হ্যাঁ, start my video করছি। যে ওখানে লিখছে যে we cannot connect your webcam. একবার বেরিয়ে করতে হবে নাকি সেটা বুঝতে পারছি না। এ, হচ্ছে না, দাঁড়াও। হ্যালো, ওয়েবক্যামটা কেন আসছে না বুঝতে পারছি না। বারবার দেখাচ্ছে
কি দেখাচ্ছে
Screen
স্যার
share হচ্ছে, sir.
we cannot connect to your webcam. Is the webcam installed properly? Okay.
ওটা স্যার
আমার তো
ওয়েবক্যামের সঙ্গে স্যার কোনো কানেকশনের গন্ডগোল হচ্ছে টেকনিক্যাল কোনো ফল্ট
হ্যাঁ, একটু আগেই তো
স্যার
ছিল।
আপনি হ্যাঁ হয়তো
হ্যাঁ,
কোনো কারণে হয়েছে
এইবারে দেখো তো।
না, স্যার আপনার আসছে না। আপনি স্যার পিপিটিটা ইয়ে করুন, দেখুন শেয়ার করুন।
হ্যাঁ, এইবারে এসছে মনে হচ্ছে।
হ্যাঁ হ্যাঁ, এসছে এসছে। ইয়েস স্যার, ইয়েস স্যার। হ্যাঁ স্যার।
ওকে, just a minute. পিপিটিটা এসছে?
হ্যাঁ স্যার।
হ্যাঁ স্যার
হ্যাঁ স্যার, এসছে।
স্ক্রিন করে নিন
ওকে, স্টার্ট স্যার। স্ক্রিন স্যার।
ওকে।
ওকে স্যার।
Good morning. Good morning.
convey my sincere thanks to the organizers, especially Dr. Patro and Dr. Mondal for giving me this opportunity. ভয়েসটা এরকম হচ্ছে কেন? হ্যালো
হ্যালো
হ্যাঁ
স্যার,
স্যার বলুন।
কেটে যাচ্ছে।
ভয়েসটা ইকো হচ্ছে কেন বলুন?
স্যার আপনি আর একটা স্যার
আপনার কি দুটো খোলা আছে স্যার?
এটাই তো বুঝতে পারছি না।
আমি দুটো দেখাচ্ছি। একটা স্যার বন্ধ করতে হবে।
আমার তো একটাই খোলা আছে।
স্যার আপনি বন্ধ করুন, আপনার পাশে দুটো সিস্টেম দেখাচ্ছে।
ওই আগে যেটা খোলা ছিল
আচ্ছা মনেদা, তুমি রিমুভ করতে পারো একটাকে, মানে তোমার এন্ড থেকে যেটা স্যার কথা বলছেন ওটা বাদ দিয়ে নেক্সটটাকে রিমুভ করে দাও।
দেখো তো, আমার তো এখান থেকে সমস্যা হচ্ছে।
না আমার এখানে
এবার দেখুন না,
হ্যালো,
এবার দেখুন প্রবলেম হচ্ছে কিনা।
ঠিক আছে আমি স্টার্ট করছি, যদি ইকোটা চলে গেছে। হ্যাঁ
হ্যাঁ ঠিক আছে, কন্টিনিউ স্যার।
Okay. So, good morning to all of you. So, first of all, I convey my thanks to the organizers for giving me this opportunity, especially Dr. Patro and Dr. Mondal for inviting me and share with you. I'm happy to with you today. So, my topic of my presentation is deterministic for a deterministic and uncertainty-based model for infectious disease modeling for SARS-CoV-2. So actually, all of you know, due to these pandemic situations, worldwide, the researchers and scientists are trying to develop some models for actually look the behavior of this pandemic, because this is people have already developed several mathematical models for different infected disease, but this disease actually still today there are some uncertainties or ambiguities of different modeling, and some because people still today do not know what is the actual remedy before the vaccinations comes. But maybe people have developed some mathematical model by which they can interpret something, say maybe some quarantine policies, some treatment policies, some lockdown policies. So many things already developed. Here also we are trying to develop some model for this type of pandemic like SARS-CoV-2. So initially we tried to develop a deterministic model where we consider the parameters, system parameters and variables are deterministic in nature. And then we have tried to develop a fuzzy model also for similar type of fuzzy models for the SARS-CoV-2. So actually, my previous speaker already gave some basic ideas of infectious disease, how to develop the mathematical model for those infectious disease, and how to solve that part. So I am not going to the detail of that initial mathematical model. So how develop the people have developed the mathematical model for this type of infectious disease. So I just quickly go through that part, and then actually what are the model we have developed and how the solutions behaves. So that part is more important here. So my today's presentations, basically I give you some background, that is how the different types of models are there. That part already covered by my previous speaker. So what is SIR model and SEIR model? So that part I just quickly finish, and then our proposed model, that is SEIAR model. Actually, all of you have the ideas. So nowadays, for this, for handling this SARS-CoV-2, actually there are two types of infectious infection is there. One is which are symptomatically infected people, and which are asymptomatic infected people. So we consider here the infected part in two groups, that is which are symptomatically infected, which are asymptomatically infected, and we develop our model. And initially, when we developed this model around 2 months back, actually we considered, because at that time in India the number of deaths is very small, so that's why we are not considering the dead population separately. And when we develop that fuzzy model, maybe after one and a half months, then we consider the death part is separately and developed that SEIARH. D, H means that home quarantine, and D means that death part. So we develop another model. So, and also we consider some basic parameters already by the previous speaker. There are some important parameters, that recovery rate, death rate, and other those parameters we consider as fuzzy variable, and we develop the corresponding fuzzy model also, because that parameters are very much uncertain. So in this way, we develop two types of mathematical model and solve those mathematical models. So in this lecture, actually, my main intention is these two models. So before going to that, the initial part already, I think Dr. Mondal has already shown this part. So I just what is epidemiology? What are the basic terms? Actually, how to define that epidemiology, and so on. So that I just skip. So the study of the distribution, actually there are different definitions for epidemiology, and the science of infected disease, their propagation and prevention, that is given by the Stelbers. And then the study of distribution and determinants of health-related states. Actually, it is most widely accepted definition by J.M. Last in 1988. So this is the study of the distribution of determinants of the health-related states or events in specified population, and the of control of health problem. So maybe I just keep those part because these are initial. So what are the aims of epidemiology? That is also covered by Professor Samuel Mondal. So I am just skip. So basically that infectious disease are two types. That is also by my previous speaker. So acute infectious disease and chronic infectious disease. But most importantly, we divide the whole population in various classes depending on their level of pathogens. When there is no pathogens, obviously those individuals are in the category of susceptible class. And once the pathogen of disease is transmitted to the susceptible host, then they are basically known as the exposed class. And once the pathogen level in the host grows in such a way that it causes cause of infection of the host belongs to the infectious class. And obviously people have some immune systems, they clears the parasites, and those are in the recovery class. So basically these are SEIR, the concepts of these different classes, and people have developed SEIR model. So the S means susceptible, E means exposed, infected, and recovered. So just basic mathematical model part also Professor Mondal has already told. So the total population N is divided into 4 categories here. X is the susceptible class, Y bar is the exposed class, Y is the infected class, and Z is the recovered class. So N is this. So in most of the studies, researchers have considered the fraction of population as given by SEIR. So S is basically X by N, E is Y bar by N, I is Y by N, and R is Z by N. So here we shall see more simple mathematical model without considering the model transmission. So when we develop any model, because maybe historical development also shows Professor Mondal. So there maybe people have started first SI model, then SIR model, then SIS model, SIR model, SEIAR model, and so on. So, and then people have considered both birth and death rate, and developed different models and so on. So every model, so people have considered the basic assumptions. So what are the basic assumptions? We shall make some general assumptions which are considered for all those models to look at some simple models before taking the specific problem. So every model have some assumptions. So obviously the disease is transmitted by contact, maybe direct or indirect, maybe through persons or maybe another living creatures in the earth. So there are no later period for the disease. That means once you contact with one person, that disease is transmitted instantaneously. There is no latent period. So all susceptible individuals are equally susceptible. So there are no difference between the susceptible persons. The population size is large enough to take care of the fluctuation of the spread of disease. So deterministic model is considered. So the population under consideration is closed, has a fixed size. So SI model already professor has already told, but here the most important is, here it is assumed that the whole population is only two classes, susceptible and infected. That means once if people is infected, then it remains in the class of infected. So, but this is not the real scenario. So so infected persons also may recover and from the disease. So that is the most important issue. So obviously people have developed after recovery of infection, so SIS model. So that means from S to I, then I to S again. So here one important parameter is that is recovery rate, that is gamma. So that belongs to the one of infectious period. So that means there may be some infectious period like SARS-CoV-2, maybe people have identified, so 3 weeks maybe the infectious period. So in that case, the recovery rate is like this. So 1 minus infectious period. 1 by, sorry. It takes to be constant where infected period, that is time span in the infectious class. So if we consider this infectious period is fixed, so obviously this parameter recovery rate is constant. So here the model is very similar to that. Already Professor Mondal has told you. So then we solve it, and one of the important thing is here one new parameter, that is R0, that is very much important. So I just that R0 is basically called the reproduction ratio. Sometimes it is called reproduction number. So when we solve that SIS model, so the solution is like this. So here already Professor Mondal told you another things. When we solve such type of problems, there are some equilibrium points. So how to determine those equilibrium? That is also important. So here also because for that stability of that model, or so that equilibrium points are important. So here we solve it and determine this A star and I star. So for the endemic equilibrium. So, and obviously from that equation, that is feasible if R0 is greater than 1. So that is also described by Professor Mondal. So here the next model is SIR model, that is also described by Mondal, Professor Mondal. So the conditions that initial conditions with that those initial conditions where S0 is greater than 0, I0 is greater than 0, and obviously the initial recovery is 0. So if S0 is less than by beta, then initially the rate of change of infectious is less than 0. That means it is dies out. So obviously the infection is invade if S0 is greater than 0, that is it is gamma by mu. So that inverse of this gamma by mu, that is called the basic reproductive ratio, or sometimes it is called reproductive number also. So this basic reproductive ratio is very much important parameters. It is defined the average number of secondary classes among the average of primary cases in entirely susceptible population. That means the rate at which the new infections are produced at infectious individuals and entirely susceptible population. So it is of So if S0 is approximately equal to 1, so when you consider whole the populations is more or less susceptible population, so then the disease will spread, and obviously R0 is greater than 1. And the disease is transmitted to more than one host, it will be spreaded. So obviously for R0 depends on the disease of the host populations. We know some infectious disease already in our country or in the world. So that is TB in the cattle, influenza, smallpox, measles, etc. So we just look everywhere R0 has some value that is around 2.6, around 3.4 the case of influenza and so on. So I think you already remember in the by the previous class. So obviously the basic reproductive number, if R0 is less than 1, then disease dies out. If it's greater than 1, so this is inverted. So obviously there are two important points when the what are the outbreak dynamics and what is the disease control. So disease control is the most issue in most of the models. So actually what are the threshold target, and is there any vaccination is available or not? I think these are similar. So people have defined another parameter that is called effective reproductive number. So what is the concept of effective reproductive number? So this is actually R0 into S by N, that is the ratio of susceptible person. Actually it is X by N. S is the susceptible, so that's why I write S. Actually it is X by N, that is S. So here endemic disease with an equilibrium point. So obviously when R effect is 1, so obviously N star by N, this is equal to 1 by R0. And graphically we can show this endemic disease. So obviously that horizontal axis represents the time and the vertical axis for the new case. So obviously you just look, this blue line actually show you the number of susceptible persons, and red line, this is number of infected persons. So obviously the number of susceptibility decreases when the number of infected persons increases, and obviously at some time this R effect is 1. So before that equilibrium point, so R effect is greater than 1, and after that R effect is less than 1, and then the infected slow down with the time. So this is basically called R control. So nowadays, I think you are sometimes heard about this hard community and other things. So how to develop the hard community? So there is a ratio, that is the number of people. Certain number of people are infected. Then maybe the society have developed some hard immunity. There is, in that case, after that maybe there is a chance to recover. Rate of recovery is increased. So it is sufficiently high proportion of the total population is immune. That means the high proportion of the populations is immune, then R effective will below 1, and maybe the disease cannot be circulated more. So it remains susceptible for the protect by the herd immunity. So the main target is, so how to develop the proper model, how to develop the model, and from that you can predict. So what should be the R effect value, that so that it is less than 1, and maybe people have the herd immunity. So therefore here this parameter, that is R effect, that is also very important. So we need to apportion, that is 1 by 1 minus R0 to be the immune. Okay. So obviously here for SIR model, that is already described by Professor Mondal. So here you just look, if we consider this DS by DR ratio, that is the rate of susceptible with respect to recovery, that is from the differential equation. It's a very simple differential equation. So from here we can solve it, that ST equal to S0 e to the power minus R0 by RT. So obviously from this differential equation, it is very simple that endemic builds up and it slow down when RT increases. So there will always be some susceptible in the population, that is ST is greater than 0. So obviously when endemic is breaks, so maybe we can consider that infinite time. So that S infinity, that is represented from the previous equation. So it is the final proportion of individuals recovered, the total number of infected population. So we can assume that for the given S0 greater than R0 from previous equation, and we determine the roots between 0 and 1. So this simple equation can be solved either numerically or maybe approximated by the small values of R0, R. This is very simple things that are already described, and maybe from the graphical representation, you just look, the more important thing, how when the time grows, how the proportion of populations is susceptible, infected, and removed. So from these three graphs, from these graphs, so it is very clear. You just look from the black, it is susceptible. So initially, the number of susceptible is very high. When time grows, the susceptible persons decreases, and obviously the infectious or number of infected people increases. So after a certain time, that infections also that is the equilibrium point, and it goes to its peak and then decreases. So obviously the removal curve or the removed curve, so that is represented by this blue line. So initially it was very slow and then slowly increase and then increase rapidly. So that mathematical part, I think this part is also described by my previous speaker, so I'm not going to the detail. So from the right hand curve, you just look, it is the proportion of population with respect to time. So for different values of R, so I already told you that initially the value of R0 is high. So when like R0 is 10, you just look, the infectious disease is more peaked. Then again, if R0 is 5, then it is less peak, R0 is 3 less, and R0 is 2 lesser, and so on. If R0 is around 1 and less than 1, then it is dies out. So this is very simple concepts. So similarly, there are some people have developed some models where they consider some stochastic effects. So obviously for the stochastic effects, these curves are not very smooth. So it is obvious. So in that case, the curves are like this. So I'm not going to the detail of that part. So, and Professor Mulder already told this part also. There are some host demographic. That means we, maybe in the previous models, we should not consider the births and death rates. So here, if we assume the maybe the one parameter that is mu here, so that is the rate of change of birth. Initially, we consider both birth rate and death rate are same. So we developed a similar model. So that for that disease-free equilibrium and some endemic equilibrium that is also described by my previous speaker. So here S dash I dash R, this is disease-free equilibrium. So obviously S0 value is 1. And so in the other case, A star, I star, R star is the endemic equilibrium. So clearly R0 is greater than for endemic equilibrium. So maybe that's mathematical part is very similar to my previous speaker. So now, because our model is basically developed in with respect to this SEIR model. So basically only thing here we consider this I part is into two separate class, that is some are asymptotically infected, some are symptomatically infected. So transition of disease start with a low number of pathogens. Here initially we consider these three parameters, lambda, mu, and nu. So this is rate of exposed class. This is mu is the rate of progression of infectious states, and gamma is the rate of recovery. So these are the three parameters. According to these three parameters, the model is developed. So ds by dt, you just look how the susceptible decreases, how the rate of decrement. So for the so this part is plus and sum of exposed to infected. In this way, we have developed our model. So this is very simple thing. So for the hard immunity part, so actually already I told you about the endemic cycle. So this is very important. Maybe people have developed some model nowadays when the herd immunity prevents. So it may be though after some time, maybe for a population the herd immunity will be developed. So after that, maybe it further outbreaks. So here the graph is shown. So maybe after some time there is a, because there are some disease. So if you look after that endemic disease of say measles, like Europe. So in that case, it goes a very long time. It may be after a few years, maybe after 5 years or after 10 years. Again, though the people have the herd immunity, again the that infectious comes and maybe up to some peak, and again. So there are some models where people like this. So here this measles in London. So you just look, every after 10 years they have some peaks. So maybe after 30 years only that dies out. So these are some pictures. I just maybe after the vaccination era also it dies out. So before going to our model, so the most important part is, because when we develop some such type of biological model for mathematical model, actually we need some basic things. That means the first things is how to when we develop a model, how to build a model, we need the most important things. But what is your data? So that means how what is your population, how much susceptible persons you consider. Obviously we should not consider the whole population from the India. So obviously we consider a sample or maybe a large sample from the whole population. So we need some data. So obviously that may be the individual clinical data, maybe the population data, maybe the epidemiological data. So these three are very much important here. So what is the clinical data? It may be the latent period. So what is latent period? That already I told you. So this is time from infection to transmission. For two transmissible. So how long he can transmit the germs? So that is infected period. So how much time that person is infected, and immunity. So how effective and for how long? So that is also very important. So similarly, the population data. What should be the population size? So it may be if we consider the whole India, its population is 138 crore. But when you develop some mathematical model, so it is really very difficult to handle whole if we consider the whole population. So maybe we consider sample populations, maybe how much are basically those people who are actually checked. So whether he has those viral effect or not. That means because every day government has trying to number of checking. So how much populations are there who are basically infected. So sometimes maybe we consider all the peoples who are coming from different states to our state. So we consider all are susceptible, as well as those peoples who has already checked. So in that way, maybe people take different populations with different size. So obviously we should incorporate the death and birth rate, survival, immigration, and immigration. So how much people comes from different country to our country? So how much are from here? Rate of contacted between the population groups. So how much contacts are there with the different population groups, and so on. So similarly, the epidemiological data is also important. So what is the transmissibility rate? That is R0. Similarly, it may be density dependent. It depends on seasonality and other things. So there is another type of data maybe we consider, that is whether the data are maybe the time series data or maybe some other types of data. So maybe I'm not going to that detailed part. So I'm going to our model directly. So maybe yes. So maybe these are all are basically the basic things are already clearly described by my previous speaker. So what are the further consideration here? The above models are very general in nature. It may be those models as a black box. These are very well-known models. In fact, the structure of a disease plays an important role in the modeling. Sometimes some disease comes where it is very difficult to make those assumptions. So what type of assumptions we should consider to actually develop such type of mathematical model for that disease. It may be noted that a disease can be transmitted directly or indirectly. Some are directly by some viral agent, some are directly by some bacterial agent and other things. So therefore, the model for most of the communicable disease required further consideration in the following ways. So now I just go to directly our proposed model. So in our proposed model, basically we named it as a ACIAR. Why ACIAR? I already told you. Some are asymptotically infected, some are symptomatically infected. So here we consider the suscepted class as a constant recruitment rate. That is, we consider these variables. I just quickly show you that graphical representation that is very much helpful to you. A susceptible person becomes infected when they come in contact with asymptotically or symptomatically. We have also assumed two types of recovery, namely the natural recovery as well as recovery after the treatment. We also assume that here the removed person may become susceptible or infected due to the multiple genotypes. So these are the very simple graphical representation of our model. So this is your whole population. Some are susceptible, some are directly goes to the recovered or released. And from susceptible, it may be comes to the exposed class, and from the exposed class some person goes some are infected, some are asymptotically infected, but everywhere you just look, there is a part which are basically the death part, so we are not considering that part. So we design our graphical structure in this way. So these are the some assumptions. Basically here we consider different type of already you know those terms like home isolation, quarantine control, treatment control, and incubation period, and so on. So disease related dates, treatment response, everything already you know, at least heard about those terms. We consider those terms by representing different parameters. So then our mathematical model is very similar to the previous one. Only thing that these differential systems has 5 differential equations. In the previous one, that is 4. So ds dt, d dt, these are very simple part. I think you can easily recognize it, because those who are actually in these type of mathematical models know those. Actually, you just look, this negative part comes here, and these part, this is for some part is due to death, some part is due to recovery, and in this way we can develop this very simple mathematical model. And also for that solution that Professor Mondal already show you, so how to solve this type of mathematical model, how to check the stability, how equilibrium is important, how to control those parameters. So every mathematical model like this type of for this type of system of equations. So the first part is how to develop your model, and the second part how to solve those models, and third part is most important, that is how to control your parameter so that you can actually give some remedy or give some good solution to the healthcare systems or the health people, so that the disease can be removed easily. So that is the important point. So these are the disease-free equilibrium. And so for the dynamical behavior, there are two important points that I already told you. That is disease-free equilibrium and endemic equilibrium. For disease-free equilibrium, we check our solution, that is S1 and R1. We solve from those differential equations. Similarly, A star, E star, I star, A star, and R star. So I think these are the mathematical calculations. Similarly, for the stability analysis that Professor Mondal has already told, we determine those Jacobian matrix, and it determine the eigenvalues. So here from the eigenvalue vector you look, so that values are all are negative, so there is a stability. So now we just look what is the first figure shows. So already I told you. So here our proposal is the fixed time control analysis by taking 100 days of the pandemic impact due to COVID-19. So actually here I show you by the 5 graphs. So actually you just look that the number of susceptibility initially is very high and slowly decrease. Here from the figure, actually at that time we considered full isolation period, that means whole lockdown throughout the country. So if that is considered a long period of time, then in that case maybe the susceptibility decrease rapidly, and the infected grows maybe around first 20 days it's grow rapidly, then it goes to the equilibrium, but that is not very realistic, because in our country where the population is around 135, 37 crores. So here, whole complete lockdown in the country, it is really very difficult. So obviously here in our solution, this is basically shows what are the susceptible populations, what are the exposed populations, what are the infected populations, and infected symptomatically and infected asymptotically. So this pink curve shows the removed class. So now the next important part is that is also told by my previous speaker. So how to design the control model. So how to design those control parameters through numerical analysis. So there are very well-known techniques, that is Hamilton-Jacobi or Hamilton-Lagrange method. So here we consider these Hamiltonian functions and Lagrangian function. Then we determined the different parametric values. This mathematical part, I think maybe those who are involved with this type of research work, they may be quickly identify it. I just quickly go to those results because the results are important. So figure 2 is basically very similar to the figure 1. So here if we consider the fixed time control analysis by taking 1000 days, because already I told you there are some disease already in the history, it may be it's a long time, maybe 20 hours, 30 hours after that, because still today there are some patients, there are the TB related patients and hepatitis B, and so many diseases are there, infectious disease. So already we are with that type of disease. So obviously if we consider the long time, that is 1000 days, then the pandemic impact, so that is given in this figure, but that is not very clear here because maybe we spread those days. So but most important results maybe if we consider the figure 3, so time versus that control parameter. So if you consider only isolation, if quarantine and isolations, if we consider treatment and isolation, so different strategies if we consider. So if you consider the isolations, you just look most of those figures, because already I told you, so like a country like India where the population is very dense, number of population is very high, so complete isolation, complete quarantine, it is little difficult for our country. So maybe the most important issue where the proper quarantine, proper treatment, proper isolation, that is the most important issue. So I just show you the next figure. So actually next figure, we consider the separate population in separate way. So that means if we consider this as susceptible population, so in susceptible populations, initially we considered all those 5 different issues. That means all control. That means all control means we consider the whole isolation, whole quarantine, whole treatment. So that means once people suspected, he goes to the treatment. Once one person is infected, then all the peoples which are with close contact with that persons, they are quarantined and isolations, everything. So in that case, if all control, maybe there is no such. That means all you just look that susceptible persons is increase clear, little increase, and it may be in the top part. So, but that is not possible in general. So if we consider, you just look no control, so then this green line, that means that number of susceptibility decrease drastically. So similarly, only isolation. So because only isolation is not the issue, because few days people may go for isolations, after that they are not that is not controlled. So that means most important part is maybe the quarantine control. So if the quarantine control is most important, people just locked in their home and no one can meet with the other people. If every persons are in quarantine, then also you just look, it is close to this curve of that all control. So similarly, only for the most important part is treatment control. So once a people is, that means if government has give that all the peoples who are infected, they are properly treatmented, properly quarantined. So then only there is a possibility of increasing those susceptibility curve. We just look, that is clearly identified from this graph. Similarly, in the right hand side, that means in figure 5, we want to show, if we consider the pairwise control, that means isolation and quarantine, isolation and treatment, quarantine and treatment. And here also it is most important, if we consider quarantine and treatment, if we consider these two parameters perfectly, then you just look, those are basically coincides with that of all control curve. So that is the most important issue. So that means the proper quarantine and proper treatment, that is the most important control parameters. So if we can do it, so in that case maybe we can control that disease. So anyway, another figures, the figure 6, it is shown the exposed population. If we consider all control, no control, isolation, the figure 6 is show you. Here you just look, if we consider all control, so obviously the exposed populations is drastically decreased. Similarly, if we consider full quarantine control, that is also coincides with that curve, but only isolations or only quarantine control, only treatment control not give you that much. So similarly, if we consider the pair of control, the figure 7 shows you the corresponding graph. Similarly, if we consider this is not exposed, this is infected versus time. So infection you also look, if you consider all control, obviously the infection goes down very quickly. Similarly, for both quarantine and treatment, you just look, if you consider the pair of control for quarantine and treatment, that also is that is also drastically reduced. So that is also shown from the figure easily. But only isolation and treatment not gives you that much good result. Similarly, only isolation and quarantine also not gives you that much of good result. So similarly, for asymptomatic control, here also the same thing for asymptomatic control. If we consider those pair of controls like quarantine and treatment, you just look, that gives you very good result for asymptomatic control. If you consider only isolation, because for asymptomatic it is very difficult to make the treatment, so obviously that not that much slow down, goes down. Similarly, only isolation and quarantine, because for asymptomatic only isolation, quarantine not that much, because they may be with their home, and maybe that they can spread the disease with their neighbors and other things. So similarly, the recovery, this is the most important part. Here also we draw the graphs for that recovery control. So for the recovery control, if we consider all the controls, then the obviously the recovery increase very quickly. Similarly, both quarantine and treatment, you just look, that is also gives you the very good result, and isolation treatments also very similar way. But if we consider only the isolation and quarantine, then that recovery rate is not very good. So similarly for the here we consider pairwise, and here we consider only the individual control. So for this model, actually we consider sensitivity analysis for the different parameters. So here a lot of parameters are involved. So initially we consider those parametric values, and basically we consider those parameters from the SARS, because SARS is already a known, there are already developed some models people have developed for the SARS virus. So in parallel way we consider these models, so we consider the data from those papers. So here we consider different sensitivity analysis for different parameters for alpha 1, alpha 2, and alpha 3. So that is here the expected populations with respect to alpha. So obviously exposed populations, you just look for different values of alpha. If alpha increases, so obviously and the number of exposed populations decreases. So here you just look here in the figure 4 gives you the exposed case, but for the case of infected populations, it is not very smooth curve, obviously, because infection is always not very smooth. Maybe some are recovered, some are again infected, and so on. So I just because the time is more or less close to the end, so that's why again we consider the sensitivity analysis with respect to alpha 3. So what is the important conclusion here? So we have discussed regarding the impact of pandemic 19 and a dynamic optimal control model using ACIR model. So that means susceptible, exposed, infected, symptomatically infected, asymptomatically infected, and recovered class. So obviously, since India is a densely populated country, therefore isolation by introducing just complete lockdown, it is not very good suggestion or not very good solution. For around the consecutive 40 days might be able to control the pandemic impact anyhow. So this maybe from our model it can be suggested. So maybe 40 consecutive days is complete lockdown. People has completely isolated in their homes, but that is maybe theoretically possible, but not physically possible. However, it has also been observed that only isolation is not a good solution indeed. So this might help in controlling of a certain limit, so which might lead to some adverse impact in future. But for 100% perception, it is better to follow hospital quarantine along with the proper treatment. So that is so here our suggestion is so hospital quarantine as well as maybe in some cases for asymptomatic persons or maybe less symptomatic persons, maybe home isolations. That is our government has undertaken considering that part. So but the most important part, proper hospital quarantine is the most important point here. So identification of infected population is very much necessary by following proper testing facilities. This will reduce the exposed population further as full of population, thus home isolation might be lead to increase in symptomatic or asymptomatic infected populations. That is the most important, which might be lead uncontrollable situations as the time. So this part actually I show you that our basically that our deterministic model, and quickly I just go through by 5 minutes our fuzzy model. So actually that is the another slide. So I just share this one. Hello.
Yes, sir. Any
Just
problem?
Yes, sir.
I just share another one. This one. Oh,
Uh, Just close this window and open your PPT.
okay. Okay. And then again I share. No?
Mm-hmm. So just close this window.
Oh.
This is another windows.
Oh. Sorry. I'm sorry.
Just open your PPT.
I just open the PPT, no?
Your
This
enter
one.
screen is, yeah.
This comes, no?
A fuzzy dynamic. This slide. Okay.
Sure. Thank you. Okay. So, yeah, where the full screen?
Sir, click on slide show in top. A file.
Yes. And then from beginning, yes.
Yeah.
Okay. So actually, just look here for this fuzzy dynamic optimal control model. Actually, we consider this is based on granular differentiability. Actually, here we use one new fuzzy differentiability technique, that is granular differentiability. Okay, but here in this model, actually, we just modify our previous model. Here we consider both home quarantine and death. Actually, so that's why it is basically SEIHARD model. So the model is very similar, but here only we consider that home quarantine part and death ratio part. So actually, in this work, we presented the optimal control model for using granular differentiability, because for solving fuzzy dynamical systems, actually, we already show you this is a set of differential equations. So obviously, it's a dynamical system. So there are some techniques for solving fuzzy dynamical systems. People have already used different techniques, but this granular differentiability is a very new concept. So here we use that differentiability approach for our model. So here we create a fuzzy, actually here we consider those parameters, that is recovery rate, death rate, those parameters are considered as fuzzy parameter. So that's why it is a fuzzy SEIAHRD model. So, so using granular differentiability, we reported this disease dynamic for time-dependent disease control. So, just quickly, so the major contribution is the first thing is we developed this concept for Indian's perspective, and we use some fuzzy dynamical system to solve this type of model, that is known as granular differentiability approach. And obviously, finally, the comparative analysis has been presented to validate our result for Indian's perspective. The model is similar, so obviously you just look for this system of differential equations. Here there are 7 equations, because we consider those things. So I'm not going to the details of this granular differentiability, because people have already developed some fuzzy differentiability approach. But they have some for these methods have some difficulties. So sometimes we solve it, we solve our model, maybe that upper curve, actually that they give you some interval based result. So sometimes that lower and upper interval is that means the lower value goes to the upper. When we show you the graphical representation, there are some difficulties. I'm not going to the detail part. So we use the granular computing approach. This is a very important approach for solving those system of equations through granular differentiability. I'm not going to the details, just quickly I show the results. So because basically when we consider the fixed control analysis for different fuzzy parameters, so obviously you just look, if we draw the graphs with respect to time to asymptotically infected populations, so the graph has several lines. So actually here we consider those fuzzy parameters and divided into separate granules. So for mu equal to 1 to mu equal to 0.1, actually we divided into 10 equal parts. So for that, 10 different curves shows the corresponding results, and obviously the lower curves give you the lower approximation, and upper curve give you the upper approximation. So here this is the interval valued graphical representation for different populations, like infected population, dead populations, exposed populations, hospitalized populations, which are maybe we validate those things with Indian's perspective, taking the data from Indian perspective. So these are different types of graphs. So for fixed control analysis for U1 parameters with respect to symptomatic infected, with respect to susceptible populations, and which are the nature of those curves is very similar to our previous results. And this is the fixed control analysis for U1 in 80 days. So we consider different days also with respect to Indian's perspective. Similarly, this is for U equal to 1 for 80 days. So here we also consider the similar optimal control policies by Hamilton-Jacobi's method. Similarly, we use this Pontegari's maximum principles. I am not going to the details of that. So for numerical analysis, you just look for three different parameters only, these eta 1, beta 1, and gamma 1. Already I told you that recovery rate, death rate, and infectious rate. So we consider those parameters as fuzzy, and by using some granular differentiability approach, these fuzzy variable transform into some deterministic variable, and that give you those mathematical part. And by taking different values of those alpha eta 1, that means that fuzzy concepts here with those alpha 1, alpha eta 1, alpha eta 2, alpha eta 3, that means different threshold level for alpha beta 1, alpha beta 2, alpha.
মনিদা স্যার
হ্যালো স্যার, সমর্থিত স্যার। আচ্ছা, হ্যালো স্যার, মনে হয় নেটওয়ার্ক কানেকশন হচ্ছে।
নেটওয়ার্ক পোর দেখাচ্ছে।
কার্তিক স্যার,
হ্যালো স্যার, হ্যাঁ শুনছি।
স্যার একটু কাইন্ডলি ফোন করে
নেটওয়ার্ক, হ্যাঁ স্যারকে শোনা যাচ্ছে না।
কার্তিক পাত্র স্যার, আপনি একবার
হ্যাঁ
স্যারকে ফোন করে একটু যদি কনসাল্ট করেন কি সমস্যা হলো।
আচ্ছা ঠিক আছে।
I request to all please stay here. Maybe problem solved shortly. Sir, if you hear me, please leave and join again. ওকে স্যার লিভ করেছেন।
আমি তাকে লিভ করে জয়েন করতে বলেছি।
ওকে ওকে।
Participant, please be patient because our speaker have some network problem. He will join very soon.
Hello.
Hello.
I request to all, please keep mute yourself. Keep your audio and video button red. Keep it red, please.
Is Avantika Das means Borun sir?
উনি ভুলবশত অন করেছিলেন।
স্যার বরুণ স্যারও স্যার নেই মিটিং।
যেটা অবন্তিকা দাস আছে ওটা মনে হয় বরুণ স্যার, মানে যে আমাদের নেক্সট স্পিকার যিনি।
আচ্ছা,
হ্যালো বরুণ স্যার,
হ্যাঁ,
এটা যেটা অবন্তিকা দাস আছে এটাই তো?
এটাই আমার।
ওকে ওকে ওকে, প্লিজ
ভিডিও অন করতে
স্যার
হবে।
joining actually, his device some problem in his device, I think.
তোমার কাছে ভিডিওটা আছে তো? তোমার কাছে ডকুমেন্ট নেই?
কার্তিক বাবু, আপনি একটু যোগাযোগ করবেন।
হ্যাঁ আমি যোগাযোগ করলাম, উনি বলছেন ডিভাইসটা বোধহয় কিছু হ্যাং করে গেছিল, আবার উনি শাট ডাউন করে
কার্তিক,
Yes sir, you are audible.
কার্তিক,
audible
বলছি
sir.
আমার
Yes sir, you are audible.
প্রেজেন্ট করে দাও। হ্যাঁ, অডিবল। আমার প্রেজেন্টেশন প্রেজেন্ট
আমি
করে দাও।
করবো,
শেয়ার করে দাও।
আমি শেয়ার করবো তো তোমার প্রেজেন্টেশন?
হ্যাঁ 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 হ্যাঁ।
আচ্ছা ঠিক আছে করবো, মানে আমি জাস্ট দেখি 1 মিনিট একটু ওয়েট করে যাই, স্যার যদি ঢুকে না আবার, আমি জাস্ট এটা করি তোমারটা করে দিই।
আচ্ছা ঠিক আছে। বস।
স্যার কল করছে। Hello, am I audible?
হ্যাঁ স্যার বল।
Okay, okay. Actually, due to some network problem, our previous speaker has some problem. So I am going to the next session. Before that, actually, I forgot to introduce the previous speaker. I just want to say something about him. Actually, Professor Samarjit Kaur, who was speaking, is a professor of National Institute of Technology, Durgapur, and he graduated from Presidency College in postgraduate from the University of Calcutta and PhD from Vidyasagar University. And now he is working as a professor at National Institute of Technology, Durgapur. And he is also an active participant in Chinese Academy, having served as a visiting professor at Tsinghua University from 2009 and as a co-investigator of the sponsored project funded by the Natural Science Foundation of China at Nankai University, and has delivered more than 15 invited talks in various Chinese institutions. His academic collaboration co-authors include academics from China, Poland, Norway, Canada, Serbia, Lithuania, and Turkey. A current research interests including optimization of computing, machine learning, and financial modeling. He has been doctoral dissertation advisor of 20 students as of now, and 6 students are working currently under his supervision. He has published over 140 referred articles in international journals and author in School Scholar, and have appeared in prestigious journals including European Journal of Operation Research, Interface, Computer and Operation Research, and also Operation Research, International Journal of Production Economics, computer and industrial engineering, IEEE transaction of fuzzy system, IEEE transaction of circuit and systems and video technology, IEEE transaction of intelligent transport and system, applied soft computing expert system with application, applied mathematical modeling, etc. He served as the head of the mathematics department at NIT Durgapur from July 2011 to June 2013, July 2017 to June 2019, and also as a committee member of many administrative academic council on the campus. Presently, he acts as Secretary of Operational Research Society of India, Kolkata chapter. This was a very nice presentation by him. Actually, in this scenario, this is very much understandable in this present global scenario. So we are very much benefited. Although he is disconnected, there was no interaction with him. So we are going to our next speaker. Our next speaker is Professor Dr. Borun Das, who is now the associate professor in the Department of Mathematics at Sidhu Kanu Viswa University. He completed his graduation with gold medal at Vidyasagar University. Also, he completed PG and PhD from Vidyasagar University. His research interests are in biomathematics, inventory, soft computing, supply chain. He has been doctoral dissertation advisor of 4 students as of now, and 6 students are working currently under him. He is working in his department from 2013, and previously he was working at Jhargram Raj College. He has more than 70 publications in different reputed journals like Computational Applied Mathematics, its Asian Journal of Mathematics and Physics, Applied Mathematics and Computation, Mathematics and Computer Modeling, Applied Mathematical Modeling, Applied Soft Computing, Journal of Computational Science, Journal of Simulation, Transportation Research Part E, Logistic and Transportation Review, and also Operational Research. And his article has been cited more than 700 times on Google Scholar. So I request Dr. Borun Das to start his session. Okay, sir, let's start. I'm sharing your content.
Thank you
Let me share.
for
Okay.
thank you. Good afternoon
Actually, his
everybody for your nice introduction to me. Like thanks the organizer of this.
Is it visible?
Yes,
Yes.
visible.
Okay, okay. Thank you.
From the last 6 months, we are going through a new pandemic situation of COVID-19. A new research area come to the fields of everything, physics, mathematics, chemistry. Now,
Voice is not coming.
can I audible? Can I audible?
Yes, sir. Continue.
Yes, sir.
So from the last 6 months, a new research area comes to the
Network issue.
There are some network
like
problems.
economics, operational research, biology, physics, chemistry, mathematics, everything. This COVID-19 comes to the new points. Here, I am not going the details or illustrating. Here, I just make some idea on the effect of COVID-19 on the economy and supply chain from the data by mistakes.
Pratik sir, next slide. Varun Babu, please prompt.
Yes, yes, I am. Go to the next page, Karthik. Go to the next page.
I think there is some network problem in his area.
There is two.
Sir, slide number, sir.
Line number 2. Next slide. The first slide.
Next slide. Okay.
Now abstract is there.
I am not visible there.
I am not seeing it.
Sir,
Is it
heading,
not
please.
visible to you?
Oh.
You want abstract or introduction?
Introduction.
This is introduction. Instead of that, the abstract. Very network.
Karthik sir, introduction slide আসুন. Okay.
Okay.
Varun Babu, continue, please. আপনি দেখতে পাচ্ছেন না? স্যার, আপনি গুগল ক্রোমে ব্রাউজারে আসুন. আপনি মোবাইলে আছেন? আচ্ছা, আপনি কি নিজেকে দেখতে পাচ্ছেন? স্যার, আপনি মোবাইলটা ঘুরিয়ে নিন, সম্ভবত দেখতে পাবেন. মোবাইলটা রোটেট করে নিন. ও ল্যাপটপে.
You just pin up on the name my Kartik Patra.
দেখা যাক তো কথা.
Introduction.
Borun. Hello. বরুণ স্যার শুনতে পাচ্ছেন?
স্যার, একটু দেখার প্রবলেম হচ্ছে, সো স্যার একটু ঠিক করে নিন. আমরা 1 বা 2 মিনিট ওয়েট করি.
Participant is
বরুণবাবু, আপনার এন্ডে নেটওয়ার্ক ইস্যু আছে. আপনি যদি ভিডিওটা অফ রাখেন, আশা করি ভয়েসটা ক্লিয়ার আসবে. আপনি যদি ভিডিওটা অফ করে রাখেন, অফ করে কথা বলেন, হ্যাঁ, তাহলে ভয়েসটা ক্লিয়ার আসবে আরো, মেবি. স্যার, আপনি ওয়েবেক্স স্ক্রিনটা পাচ্ছেন? ওয়েবেক্সের উইন্ডোটা? আপনার এন্ডে কোনো সমস্যা হলে স্যার বলুন. স্যার, এখন ঠিক আছে, আপনি কন্টিনিউ করতে পারেন স্যার. আচ্ছা স্যার, আপনি নিচে আপনি গুগল ক্রোমটাকে আছেন না, ওয়েবএক্স অ্যাপ ইনস্টল করেছেন আপনি স্যার?
এতে করেছি, আমাদের ওয়েব এক্সে করেছি।
হ্যাঁ, ওয়েবএক্স অ্যাপের আইকনটা শো করছে নিচে স্যার? নিচে আইকন শো করছে কোনো? একদম নিচে দেখুন। এটা ব্লু কালারের না ইয়েলো কালারের কি আইকন? হ্যাঁ বলুন।
জয়েন মিটিং,
জয়েন মিটিং নয় স্যার। আপনি তো, আপনাকে তো দেখা যাচ্ছে আপনি আছেন। আপনি গুগল ক্রোমটা ওপেন করুন স্যার, ক্রোম ব্রাউজারটা। হ্যাঁ স্যার, দেখুন আপনি ওখানে আছেন, মানে ক্রোমের একটা উইন্ডোর মধ্যে আছেন। আপনার কি ক্রোম ওপেন আছে, ব্রাউজার ওপেন আছে স্যার নিচে, মানে খোলা আছে ব্রাউজারটা? আচ্ছা স্যার, লিভ করে জয়েন করতে পারেন, বেস্ট হবে। কার্তিক স্যার।
হ্যালো হ্যালো, হ্যাঁ
হ্যাঁ, হ্যাঁ স্যারকে একটু বলুন লিভ করে জয়েন করার জন্য, স্যারের একটু বুঝতে অসুবিধা হচ্ছে।
ঠিক আছে, আমি ফোন করছি।
হ্যাঁ ফোন করে বলুন পুরোটা লিভ করে জয়েন করার জন্য।
এটা নিয়ে
হ্যাঁ, স্যার আপনি একটু লিভ করে জয়েন করুন, পুরোটা ক্লোজ করে।
আপনাদের একটা পিপিটি পাঠিয়েছি, ওটাতে আপনাদের সাইড থেকে যদি করতে পারেন দেখুন। প্রেজেন্ট
স্যার আপনার এন্ডে প্রবলেম হচ্ছে স্যার, কার্তিক স্যার?
না না, আমি তো শো করছি, এবার সেটাতে কোনো সমস্যা হচ্ছে কিনা বুঝছি না তো।
না স্যারের হবে, আপনি একবার প্লে করুন, এবার হবে।
আমি করবো প্রেজেন্ট।
আপনি play করুন স্যার।
at the present time, I am audible to all of you.
ইয়েস স্যার, ইউর অডিবল।
This is from the coronavirus disease as COVID-19. The first case of the coronavirus was reported in December
স্যার পিপিটি কি দেখতে পাচ্ছেন আপনি?
2019. আমার ল্যাপটপের ভিডিওটা খুললাম।
ওকে,
In the
কন্টিনিউ স্যার।
city of China, which is known as a major transportation hub of China. After the spread of COVID-19, many countries have shut down their seaports, airports, have banned the import and export activity. Also, China is the major distributor of the raw materials, which affects the manufacturing activities across the globe due to lockdown. India is the developing country due to the COVID-19 split the cases reported in the India government has lockdown for 41 days, which affected manufacturer activities and majorly the supply chain and economy of the country. In the present paper, we have discussed the effect of supply chain economics, transportation, demand, etc. in different parameters to the on the COVID-19. 2 days ago, we are trying to research on the substitutable or complementary items. But now, in the COVID-19 situation, the substitutable and complementary item phenomena has just gone away. Instead of that, here a minimum requirement item is coming. So in this way, in transportation problem, there are we consider transportation cost and fixed cost due to the toll tax, road tax, etc. But due to the COVID-19, here we avoid some path where the lockdown pandemic situation occurred, so we cannot move there. So this type of phenomena also come. Now we go to the next four. Impact of COVID-19 on Indian economy. Great economist Willis has suggested the concept of trade business cycle after the Great Depression. The four stages of trade cycle is considered to measure the growth rate and real GDP. International Monetary Fund was had projected the GDP growth at 1.9%. This shows the gross poor performance of India after the realization of 1991. In the fiscal year, and government has distributed the whole economy. Now to the page 5. Page 5 shows the India's growth trajectory since 2011. Here you see that in 2011 and 2012, India's growth trajectory decreased, but after that, 2012-13 its growth 16, 17, then decreased at 2017, 2017, then again decreasing to 18, 19, 6.81. But in 2019, 20, India's growth trajectory fall at 4.78. Demand side drop. That I say here because the huge uncertainty and falling market to double hundred of business that disturb the entire chain of production in human cycle. It includes the various services provided by the Indian government and private sectors such as tourism, hospitality, aviation, are major sectors that are facing maximum loss in the present crisis. Tourism that account 9% of GDP will decline at least in next 2-3 quarters. If we go to the table number 7, supply side impact. Some targeted industries in the supply side go for the shutdown that are the marginal farm, India being the highest exporter of raw materials and imports source of goods that are required for the intermediate and final goods are on pause now due to the delay in supply of goods from China. Sectors such as pharmaceuticals, automobiles, electronic chemicals, products, etc. are facing a shortage of requirement component. As China account for 27% of India's automotive part imports, India imports about 85% of active pharmaceuticals ingredients from China. And we group After there is possibility of shortage there will be the price will go on things due to the down and global pandemic that business entering in production cycle. The development model consists of framework. In recent studies, it has said that maximum time from the onset of coronavirus infection hospitalization in 10 days to is in this period to 14 days. So in this 14 days, like containment day, there may be 14 parameters like susceptibility, infected, recovery. There may be in 14 days, there may be 14 times of parameter, 14 times of parameters exist, and these 14 type of parameters together form new mathematical equation dx to dx1 pt and equal to b, and every parameter has positive or negative minus just some negative parameter of these exporting. Again, there may be positive some another 14 parameters, and there may be minus some 14 parameters. So this will be a complete coronavirus model in for the 14 quarantine days. We may use 14 parameters. This, although COVID-19 pandemic had spread to 190 countries worldwide other than China, 10 European countries have been the most affected. India's total export growth from April 2019 to March 2020 is shown in the following graph in red color. These are the worries and these are the and hello. Oh, okay.
কার্তিক স্যার
হ্যাঁ হ্যাঁ শুনতে পাচ্ছি। হয়েছে ডিফারেন্স শেষ করছে নাকি? ইজ ইট ফিনিশড? ওকে ওকে।
Thank you all again.
Okay, thank you. Am I audible?
Yes, yes.
Yes, sir, continue.
Okay. Actually, due to some network problem, third speaker was not audible very clearly. I'm sorry for that. And so this is the end of the lecture session. So now I want to go to the finishing touch, and so I request our Professor Rahul Mondal to give a vote of thanks and to finish the webinar.
So, good afternoon, everybody. We are at the end of the webinar. There was some technical issues, but I hope we all have enjoyed and been enriched by the valuable speeches given by our respected speakers. I must express my sincere thanks to our honorable principal for her continuous support. I would like to thank advisory committee members for their valuable suggestions. We are very thankful to our IQAC coordinator for encouraging us. Also our colleagues, especially Dr. Patro, who took the initiative, and all the participants. Their participation made the entire webinar successful, and that's all from us. Thank you. Hello.
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 Huh?
Hello.
Yes, sir. Audible.
Hello. Am I audible?
Yes, yes.
Okay.
I have finished my speech.
Okay. Okay.
Hello.
Hello.
Yes,
I
sir.
have finished
Okay.
my
So this
speech.
is the okay. Okay, this is the end of this webinar, and I also want to thank everyone, all the participants and all the speakers for their valuable speech, and to the participant for their participation. Okay, we will end here. Is there anyone who want to share anything, or we will end here?
Please unmute if you have any.
Any question or anything?
If not, then
Okay, if not, then we will end here. Finish the meeting.
okay. With your kind permission, Malaida will end this meeting.
Okay,
Karthik sir.
okay.
Okay, Karthik sir, may I end the meeting?
Okay, you can end now. I think yeah, you can end now.
Okay,
Okay. Malaida, please end. Thank you.
Okay.
have a good day.